All right, guys, big day today. So we are on page maybe 75. All right, today is part 2 of calculus. So what we have done for the first half, really, and we're at about the halfway point. I know it doesn't feel like the halfway point of the year, but we get finished in early March with this course, and then we review it for 2 months and get you really ready for an AP test. So what we're starting now is integration. So what we have done so far is derivatives. We have taken a function, taken its derivative, and gotten the derivative function. What we're going to do now is go backwards. So integration is an antiderivative. Okay? Now, we have all these derivative rules. Now, the reason this becomes maybe for some a little bit more complex is, do you know how when you apply, say, something like a product rule, you do the first, do second, plus second, do first, right? And you see the product rule there, but then you simplify it and clean it up and it looks completely different. So I can't really tell that a product rule got me there. Are y'all with me? So sometimes getting back to where I began becomes more difficult. In fact, there are some integrals that we will not be able to take while we're in this course because it's like Cal AB, right? It's like Cal 1. And there's Cal 2, there's Cal 3, there's tons of calculus. So we're going to learn a lot, and I mean, quite a lot, but we're not learning everything. There are certainly integrals that I will not be able to take, basically functions that I cannot figure out what original function they came from when somebody derived them. Okay, so what we're going to do is learn some rules. Just a handful of them. You'll see them on a sheet. But a lot of our functions that we're going to try to integrate won't look like these rules. They won't. So our task is to make substitutions so that they do look like the rules, and then we can apply them. So the whole course, we're not going to do that today. Today we're going to be very basic. But what we're going to be learning is how to basically go back, except it's really not going back. We're just starting with the function, but it'll feel like we're going back to the function that we originally took the derivative of. All right, so again, we're going to have a function. We take a derivative. What we're doing today is taking this function and integrating it, or taking the antiderivative and going back. So I'm going to start you with a couple of functions right here, right? And I'm going to take the derivative of them, and you can see if that's a function, that's just a polynomial, right? So to take the derivative, we would apply the power rule. And your power rule is take the power, multiply, decrease the power by 1. And you can see me doing that over and over. And then what happens to the constant? It goes away. All right? Now, right here, if I take a derivative of a 3 tan, you see that I brought down the 3 and took the derivative of the tangent and got secant squared, right? And then you take the derivative of the x and got 1, so you didn't bother writing anything. And then technically dx, but we didn't. And then right here, you can see, oh yeah, I dropped the 8 down. And what's the derivative of the natural log? And some of you are like, oh, I forgot that. But you take the whatever you're logging and put it in the denominator. Remember that? And then you take the derivative of the denominator and put it in the numerator, and that's 1. And then you end up with 8 over x. Okay, so these are just 3 random derivatives I took. So what we're going to want to do now is our process is, what do we do to actually take this new function, this derivative function, although I might not call it the derivative function, I might call it G or big F or anything. But take this function and go back to where I was. Okay, so if you think about the process just with a power, this first one, if I multiply by the front and then decrease the power by 1, going backwards, what does it sound like maybe I should do? Add 1 and then take that new power and divide it. And that is your integrated kind of going backwards rule. So right here, if I have this 12x cubed minus 4x plus 5, to get it back, I'm going to add 1 to the power. So this is what you do when you have powers. You add 1 to it, which makes it x to the 4th, and then take that 4, that new power, and divide the leading coefficient by it. And what do you end up with? 3x to the 4th, which is where I began. Look at the next one. The next one I had negative 4x, which is technically a 1, right? So I add 1 to that and get x squared, divide the negative 4 by 2. So you can see I added 1 to the power and then took the new power and divided that in there and got negative 2x squared. And sure enough, that's where I started. Now, the 5. The 5 is sitting there by itself. But technically, couldn't you argue that it's 5x to the 0? Because x to the 0 is 1. So if I have a 5, I basically say, well, if it's 5x to the 0, I can add 1 to the 0 power and then divide the 5 by 1. And what am I left with? 5x. But I got to be honest with you. All I do when I integrate a constant, I just put an x on it. It's just easy to remember that. Just like most of you probably didn't do the power rule when you saw 5x, right? You see 5x and you just grab the 5 when you took the derivative. Well, go backwards the same way. If you got a constant, put an x on it. Here's the problem. How do I get that -4 out of thin air? I can't. And if you're in physics, you've probably talked about this already, especially if you're physics C, right? So I don't know. And the problem is I have no idea what that constant is. The constant might be 0, might be -4, might be +50. And think about it. No matter what that number was, when you took the derivative, it was going away, right? So what happens when I integrate to get back to this function, I get a whole family of functions, right? And if you really think about it, this right here, this C value, really represents a y-intercept. Because if x is 0 here, what happens? All that goes away. So that y-intercept could have been anything. Now the actual function is going to look the same, right? X to the 4th. It's some wiggly polynomial, right? But I have no idea where it crosses the y-axis. And you kind of got a taste of this. Do you remember when you were sketching? Remember we were doing all the curve sketching? And I gave you like the derivative of f and asked you to find f? And you remember that like it didn't matter where you started? You just had to make it look that your shapes all look the same, but it might have been high, might have been low. Why? Because we have no idea what the y-intercept is. That's what's happening here. So what we're essentially doing is finding that function, that original f, when we're given an f prime. That's what taking an integral is. And when you have a polynomial, you're going to be applying the power rule. And that's what we're going to be focusing a lot on today. But there's other things too that we could do. So this is how it will look for you right here when I ask you to find an integral. You'll see this little funny little S looking thing, but it's not an S. It's almost like some people have it vertically and it has like a little hook on the top and a little hook on the bottom. Some people, it's a slight slant, little hook on the top, little hook on the bottom, but it's not an S. Okay, I know a lot of people, when you draw them, you get a little sloppy and it's like, people will go, oh yeah, the integral of 12. Don't do that. That's not an integral. That's a big S. Okay, so when you do this, try to have a decent looking, and you can practice, but try to have a decent looking little integral sign. They look like that, or you can make them vertically or whatever. And it doesn't have to be perfect, but think it's a little bit straight in here, right? A little bit straight with a little hook on either end. You tracking with me? So what you're going to see is a little integral, then you're going to see a polynomial, and then you're going to see this dx. Now the dx, you're going to be like, what the heck is dx? It'll mean more later when we talk about what we're actually doing. Right now, you think we're just doing an integral. We're going back to the original function, which is true. But an integral really finds a bunch of area. So when you integrate a function, you're finding the area below the curve. And how do you find area of a rectangle? Base times height, right? Well, this function is y. Y is height. dx means change in x. So what we're doing is we're basically taking a bunch of heights and a bunch of widths, and we're making a bunch of little mini rectangles to fill in under the curve. And we'll talk about this later when we get into what we're actually doing with an integral. Right now, we're just going to learn the mechanics. We're going to learn how to integrate. It doesn't really matter at this moment what it means, but that dx is important. AP is a little lax, but I don't want y'all to be sloppy. So I'm going to teach you good etiquette, right? We don't chew with our mouth open. We put the knife and the spoon on the right side of the plate, unless we're in Germany maybe, and we put it on spoon over the top. We put the fork on the left. These are all etiquette issues. So in math, I want you to have good form and etiquette. Anytime you integrate, you're going to have a little dx at the end. Every time. Are you with me? Okay, so to integrate, I basically am going to do, if it's a polynomial that is added or subtracted, not multiplied, that's different. We'll have to learn something new. But if it's a bunch of stuff added or subtracted, you literally can integrate each little part like it's a separate integral using whatever rule you want to apply. And in this case, it's a power rule. So this, add 1, it becomes x to the 4th, divide by that new 4, you can see I end up with 3x to the 4th. Add 1, x squared, divide the 4 by 2, negative 2x squared. If I have a constant, what's the easiest way to think about it? Throw an x on it, 5x, and then don't forget your c, because there's always some place where it crosses the y-axis that I don't know about, which ought to make sense, right? Based on what we were talking about earlier, because if I took a derivative of a constant, it would go away, and it's gone. How do I know what it was? It might be 0, it might be negative 20, it might be 60. I have no idea. So don't forget that c. And then there will come a point pretty soon where we're actually evaluating the area from like 2 to 10, where we're taking a separate little interval and we're saying, hey, how much area is there? And in that case, you'll see these c's go away. But for now, you got to remember the plus c on everything. Are y'all with me so far? Okay. And if you want a kind of a little proof of this, basically, we call it a derivative. A dy dx was the same thing as f prime. And kind of the way this math kind of plays out is if I multiply both sides by a dx and cancel that, you'd see this, right? You follow me? And then if I integrate both sides right here, you get an integral of dy, right? And an integral of dy, isn't that the same thing as the integral of 1 dy? Y'all with me? And then what do you do with the constant 1? You write what? 1y? Because I'm doing dy, not dx. Like, what did we do with our constant before? Like if I was integrating a 4, we wrote 4x, right? So here I integrate a 1 dy and I write 1y. Now, technically, I can put plus c. That makes you feel better. And then over here, when I integrate an f prime, well, if I take a derivative of an f and I get to f prime, what do you think happens when I integrate an f prime? I get back to f. So all of this right here gets me back to f. And again, if it makes you feel better, if I have a y plus c here and an f of x plus c there, what do you think happens when I combine these constants? What do you think? Well, they're different. They're different constants, perhaps. So what do I end up with? I call one c1, one c2. What happens when I take two constants and add or subtract them from each other? I just get another constant. That's why they only have one constant there. So what they're trying to show you through all of this, to show you that anytime I integrate, I'm going to get a constant. But if I have two constants and I move one over, it just becomes a third constant. So when you see something like this in a textbook, what they're just trying to show you is when you go through the process of integration, you're going to have this constant left over. You'll get a function, some new function plus a constant. Okay, now in calculus land that we're going to be living in for a while, what you've done so far is you started out with like a y, and you've ended up, you take a derivative and you get a y prime. You start out with an f, you end up with an f prime, right? Or maybe you start with a y, you get a dy dx. Well, when you're going backwards, they don't always say that it's a derivative. Sometimes they just call it g, okay? Or sometimes they just call it f. But they want to have a name for what it means when you go back to the original function. So what you'll see a lot of times is, okay, if you originate this g, this original function is related to g, right? So they just call it big G. So you're going to see a lot of little g, big G. They can call it anything they want, but it's kind of like this. If I start, don't let this bother you a lot, by the way, because I know it kind of can. But if I start with a y and I ddx it, it turns into a dy dx, right? And a dy dx is the same thing as a y prime. It's like an f prime of x. Are you with me? Well, if I integrate, I'll do a better job now. If I integrate an f prime like we just saw earlier, that gets me back to the original f plus some constant, right? If I integrate a y prime, these are all just different forms, I get back to the original y plus some constant. But I don't always call the function I'm working with f prime and y prime. Sometimes I'm going to call it g. So all I'm trying to show you by this is if I don't call it the derivative where you can go back to the original, but I just call it g, we say, oh, you're going back to the original, and we call that big G. Does that kind of make sense? So big G is kind of like your original function, whereas little g would be like your derivative. That's the way you're going to see a lot of this written. Are you with me? They don't have to. They could say integrated g and get a qx. Integrated g and get an s. They can say anything they want. But if they start using big G's and little g's, think in your head, oh, that big G was the original function that I started with. Yes?
Did you have like an x and then you would have a big F?
Yes. And that's very common too. So right here, what he said was, could you have like a little f there and then use a big F there? Yes. Which means you got to be really specific about little f, big F when you're doing some of this work. Okay. Now again, if there's a function there like the work we just did, then you don't have to name it at all, right? Like there's just a function, just integrate it and get your answer. Don't worry about always naming it. But you'll get more comfortable with this. But I just wanted to emphasize that a little bit as we're starting out. Go back to this next example. Do you remember how when I took a derivative of tangent right there, I got 3 secant squared x? Well, what happens when you integrate a 3 secant squared x? Well, let's talk about that. First of all, the 3 is a constant. If you ever have, a coefficient. If you ever have a coefficient, not an x, but a number, you are allowed to pull numbers out in front of the integral and ignore them, right? Just ignore them, kind of like you did when you took a derivative. You just dropped it down and ignored it and then took the derivative with coefficients. You're allowed to do that. So that 3 right there, you see that 3 and you're like, you know what's kind of bothering me? I'm going to take that 3 and just move it out to the front. So you can ignore it. When you see an integral that's not an x to a power, then I'm not going to do the power rule, at least not just yet. So what I do is I think, well, was there something that when I took the derivative of it, I got that? Yeah, tangent. This is why you got to know all your rules. If I take a derivative of the tangent, I get a secant squared, x, right? Well, then that means if I integrate a secant squared, what must I get? Plus some c. So if I integrate this secant squared right here, I am going to get tangent of x plus some c. And since the 3 is on the outside, I then distribute the 3 in. Now, can anybody explain to me why I didn't write 3c? Because it's just still a constant. Did it change? Maybe. If c was 1, it didn't. If c was 0, it didn't, right? But if c was 2, it did. If c was 10, it did. If c was -6. And because I don't know, and in some textbooks, you'll see initially, they'll put C1, and then they'll write here C2, but that just starts getting tedious. That's probably changing, more than likely it is, but it's still a constant that I don't know, right? So we just kind of start getting, I don't really call it sloppy, we just don't bother discerning between one C and the other C because it's still an unknown. So we just call it C.
And we won't get taken off of
No. Most textbooks don't even acknowledge that it's different. They may be one time, okay? All right, what about this? 8 ln x. So 8 ln x, you might look at it and go, all right, I knew that when I took a derivative of 8 ln x, I just copied the coefficient because it didn't really have a place for anything. And then I said, what's the derivative of natural log? And I should know that the derivative of a natural log is whatever you're logging goes on the bottom, the derivative on the top. So I get 8 over x. Well, what happens when I integrate an 8 over x? Well, I have to be able to think backwards that way. I go, oh, if I take a derivative of a natural log and get a 1 over x, then I should be able to integrate a 1 over x and get back to a natural log. So that's what I did. That was a coefficient, that 8. And anytime I have a coefficient, what do we say we could do with it? Swing it out front, leaving me 1 over x. So what do? I go, well, the integral of a 1 over x, again, because I know this derivative rule, the derivative of that becomes that. Well, then the integral of that becomes this, plus some c. And then since the 8 is on the outside, I distribute the 8 in. But again, 8c is c. Now, for anybody looking at that and going, wait a minute, why couldn't you do this? Change it to x to the -1. And if I change it to x to the -1, I could just do a power rule, right? Try it. What's the power rule tell me? It tells me to add 1 and then divide by that new number, right? So if I add 1 to this, I get x to the 0, but then I have to divide by 0, don't I? And I can't do that. Are you following me? So if it's ever a single x on the bottom, you're right, you can't do it. But if it was any other x, you could. It's x to the squared on the bottom, x cubed on the bottom. Yeah, it works great. Make it a -3, exponent, knock yourself out. Use your power rule. But not a single 1 over x.
Wait, but couldn't you also, how, if you had something that wasn't a single x, couldn't you also do the natural log? Would it be the same thing? Again?
No, and we'll talk more about that with u substitution. But, well, and again, you could try it, but think about it. Well, I'll show you. Because remember, I'm taking a derivative of something to get to here, and I'm integrating it to get back. So I think what you're asking is this. So hypothetically, what if I had a function like, come on,
It wouldn't be a constant on the top if you had it.
watch. What if I had a function like natural log of, I'll just make it x squared. Okay, so if I take the derivative of that, what do I get? X squared on the bottom, and then derivative on the top, right? Which simplifies to 2 over x. Okay, so if I integrate a 2 over x dx, what's my rule? Swing that to the front.
Which is true because of the rule of exponents. 2 ln x
Hold
is
on.
equal to
Let me do this. How about this?
But like, isn't that right though? Like, because 2 ln
Well,
x is equal to
hold on. I'm gonna address what you're saying in 1 second. Hold on. Dang it. Okay. So what if? Sorry. So go back to where I was. What if I said, and then I'll look at that. What if I said, what did I have originally? Natural log. Okay. So what if I had this? Okay. So the derivative is copy that on the bottom, derivative on the top, right? Now, this would be a little bit beyond your pay grade right here. But what if I had, like to be too, I have to do u substitution before I can show you this. I'm trying to think of a better example. The reason why what you're saying is going to work right here, the reason why you're saying that this is going to work is that isn't this the same thing as that?
Yeah.
That's why.
So you
Because that's the same thing as 1 over
you
x.
can do it if there's not something being like added to it.
Right, and you'll see that with u substitution.
Okay.
So just hold that thought. But right here, okay, so right here, the reason why, this is maybe a better example. The reason why right here, I cannot say that the answer would be the natural log of x squared plus c. This is, I think, what you're asking.
The one would. It would
Because if the integral of this gives me this, then shouldn't the derivative of that get me back to this? Shouldn't it? Because there are any derivatives. And if I take this and take the derivative of it, what happens?
Yeah, x squared on the top.
I get x squared on the bottom and what? 2x on the top, which is what? 2 over x. That's not the same thing.
Wait. So how did you even?
So this is why this is
How
not
would
true.
you even get that? How would you get that first thing from 1 over x squared?
Well, because the integral of 1 over x dx, and then I've got to move on because people's brains are exploding. Right here. So right here, this is a rule. When I integrate, this is true. When I integrate a natural log, I get 1 over x. When I take a derivative of the natural log, I get 1 over x. When I integrate a 1 over x, I get natural log. But I can't apply that here. And the reason why is, if this were true, I should be able to take the derivative of this and get back to that. But when I take the derivative of it, I don't get back to it. So this isn't true. So when you get a situation that has anything other than a single 1 over x, a single x on the bottom, you have to integrate it like this, which is actually easier because now you can do a power rule. What does my power rule tell me to do? Add 1 and divide by the new exponent. And don't forget your constant. So this ends up being what? A negative out front and a 1 over x plus c. So bottom line is, and we'll get back to that later, but bottom line is I have some derivative rules. You have to know your derivative rules. So when you're learning these, that's why I asked you to go back and take that little derivatives quiz on your assignment sheet. You may not have done that, but to go back and remind yourself of all your derivative rules. All right. So I'm going to go through a few of these. And I mentioned this earlier right here. Remember, if I integrate a little f, we normally call it big F plus c. But if I integrate an f prime, it just the integral and the derivative cancel, and I can write it as little f. But most of the time, they don't write it as f prime. They write it as f or g. So we use a big F to show the difference. All right, so just walk through me a couple of these with me. If I integrate this first one, what would my rules tell me to do? So the integral power rule tells me to what? Add 1 to the power. Now, first of all, can't I just bring the 7 over because it's a coefficient? So add 1 to the power, which gives me x cubed, and then what? Divide by 3. Okay, that works for me. And then for the next one, can't I write the -3 down? And what do I do with that x to the first? Add 1 to the power makes x squared, divide by 2. And then what do I do with the constant? Throw an x on it. And then what do I always remember at the end? Plus a c.
But is it okay if you write like 7/3?
Of course. 7/3 x cubed, totally fine. And don't worry about leaving it with negative exponents too. That's totally fine too. Nobody cares. Right here on this number 5, x cubed on the bottom. That is not a single x. So what do? Swing it up and make it a 2x to the -3 dx. Now that 2 is a constant, so I can just write that down. What do I do with x to the -3? What's the rule? Add 1 makes it a x to the -2, and then divide by a -2. And that's the only thing, but don't forget your plus c. Now, could that look a little better? Sure. I could write that as a -1 and maybe even take the x to the -2 and put it on the bottom and make it square. So this is fine, but honestly, it's probably going to be written in your book with just the 2's canceled, and it'll be -x to the -2 plus c. You tracking with me? So any one of those, whatever. All right, look at number 2. What do you think I do with a square root of x? X to the 1/2. So I'm going to rewrite that right there as the square, the integral of 2x to the 1/2 power dx. And again, work on the form. Put the dx's in there. Don't take shortcuts. What's my power rule say? Add 1 becomes a what? 3/2. So I get 2x to the 3/2. And then what do? Divide by 3/2. Now, I don't normally write divide by 3/2 and then plus c. I realize to divide by 3/2, I'm going to be multiplying by a reciprocal. So what I usually do when I see these is do this. I go 2, and then I leave a little space and write x to the 3/2, and then go to divide by 3/2. I multiply by 2/3. So you'll see my work look like that, and then maybe I clean it up and write 4/3 x to the 3/2 plus c. Y'all tracking? Okay, what about number 7? What?
Number 7.
So number 7, it's a power. So I can do my power rule. What does it tell me to do? Add 1. What happens when I add 1 or 3/3 to 2/3? Okay, so here we go. I'm going to write down the coefficient. I'm going to leave a little space, right? And go x to the 5/3. But to divide by 5/3, I'd be multiplying by 3/5. So I'm just going to go times 3/5. But remember, I'm dividing by 5/3, multiplying by 3/5. Don't forget the plus c. So I get 18/5 x to the 5/3 power plus some constant. And you do not need to change fractional exponents back into like cube roots and junk like that. Don't bother. All right, look at number 8. There's a bunch of junk going on, right? Can you look through there and say, oh, I'm going to be fine right this second, or maybe do we need to rewrite it? So I'm going to rewrite it as leave the 2x cubed. I'm going to write that as -4x to the 1/2, and then x to the -4 dx. So what's the integral of 2x cubed? 2x to the 4th over 4, which is 1/2 x to the 4th. And again, write as much as you need to. You're fine to write 2x to the 4th over 4. Then clean it up. So what about the next one? Minus 4 times. All right, what am I going to do with that x? Add 1, which gets me to 3 halves. And then I got to divide by 3 halves. But to divide by 3 halves, I'm multiplying by 2/3. And then what do I do with the x to the negative 4? Add 1 gets me to negative 3. Divide by a negative 3. And then don't forget a plus c. Is it going to look like that in your answer key? Probably not. It's going to probably look like 1/2 x to the 4th minus 8/3 x to the 3 halves minus, and it's probably going to be 1 over x cubed when you look at it. But I don't mind you writing minus x to the negative 3. That's totally fine. Nobody cares.
Wait, is
Oh, sorry. That negative 3 stays right where it is. So sorry, 3x to the 3rd. All right? So you might see it like that. You might see it like this right here. Negative. It might look like that. It might look like a negative 1/3 out front. Whatever. Are y'all seeing this? I'm running out of time. Hey, real quickly, if you do see a fraction like this, isn't it true, just to kind of show you and help you with this one, and then you're just going to do the best you can, right? Isn't it true that that simplifies to 2x squared? And be careful on this one. What do you do? Be careful with that. What do you do when you divide like bases? So what would I end up with here? 4x to the what? Negative 1/2. So if this is, you have to think that way to set it up and then apply your rules.
For stuff like number 10, should just multiply it out.
Yes. Number 10, definitely. You don't have any other rules. So FOIL this thing out. Number 11 and 12 and 13, do the best you can. But guys, I need you to start memorizing these integration rules. You'll recognize, oh, the derivative of sine is negative cosine because the integral, because the derivative of negative cosine would be sine. The integral of cosine would be sine because the derivative of sine is cosine. Start memorizing these. We're going to spend a ton of time on this, so see you tomorrow.
You told me this calculator was
Sorry?
You told me this calculator was but not slow enough to work.
No, although you could probably just want to borrow one of my 84s, they're a little smarter, faster.
It's not weeks, we're not doing homework grades.
I don't know, but you better do it.
I know, but I want homework grades to bring it up, you know.
Yeah, I rarely take up homework. I try to teach you like a college student at this point.
Yeah.
How about those mistakes?
Yeah.
Yes, like it.
You doing homework every night?
No, that's why.
Then you know your answer. Appreciate your honesty. You know your answer, just start doing it. See what happens.
Yes, sir.
Every night.
Yeah, I promise you.
When you get stuck, come see me.
We'll be holding.
Then you won't have surprises on your test.
Yeah.
Come on.
That was that.
Do what?
I could do it. I understood this process, but then on the test I was like, oh, because if I did the problems on homework, I would have got stuck
you know the
earlier.
saying, if I hear and I forget, I see and I remember, but I do and I understand. You're seeing, but you're not doing. So you're seeing it, you remember doing it. It seems like it's not a big deal, but it's almost like, what if I watched Usain Bolt running the 100 meters?
Mm-hmm.
And I'm like, ooh, I can do that. I'm not gonna make it faster. Maybe a little bit, because I can look at, oh, that's how he leaves the blocks. Oh, that's how he keeps his head down. Maybe a little bit, but ultimately, how do I do that? I get out there and do.
Get athletic. Athletics.
Start doing it, man.
Yes, sir.
Thank you, sir.
Yep.
Sorry, do you get to the calculator on the test?
Probably not this one.
No, not this one. I meant the
Oh, there's 2 sheets of paper. It'll say this on there, and I highlighted it, but the first front and back is no calculator, and then the second front and back is a calculator. I mean, you can have your calculator on your desk for it, but you have to be able to show all your work without it. There's really no need for it.
If he tries to make it feel.
Do you know what they did? That's the word.
What's up?
Hello.
How you doing?
Good.
Good.
How about you?
Not too bad.
You want this?
I didn't know that you did not like him.
We have like this thing and this. I think I got 5 of them. What'd you get? I don't know how many I missed for sure, but I think I did. Okay.
She did well in calculus.
Oh, I did. So did Lily. She got 1 point better than me. 1. Singular.
Still pretty solid.